So good evening to Dr. Alvie and everyone. Today I will do a presentation about wave equation for sound waves. So for introduction, the wave equation is a fundamental concept in the mathematical physics describing how waves propagate through various media. This partial differential equation is critical for understanding phenomena in fields ranging from acoustics and optics to quantum mechanics and fluid dynamics. The wave equation involves second-order derivative with respect for both time and position, encapsulating the dynamic relationship between inertia and elasticity within a medium. The one-dimensional wave equation, which models systems like vibrating strings or sound wave in a narrow tube, is expressed as I already wrote in this article, which is d square u over dt square equals to c squared d square u over dx square, which is in this equation u xt represents the displacement of the wave at the position x and the time t. C denotes the speed of wave propagation, which is determined by the physical properties of the medium. For a periodic elastic string, the wave speed c given by c equals to square root t over rho, where t is the tension in the string and rho is the linear mass density, which is mass per unit length of the string. The relationship illustrates how the wave speed depends on the medium's tension and mass distribution. The historical context of the wave equation is notable. It was the first derived by Jean-Baptiste Leron d'Alembert, a prominent French mathematician and physicist in the mid-18th century. D'Alembert's work provides a rigorous mathematical framework for understanding wave phenomena and laid the groundwork for subsequent developments in physics and engineering. So for the theoretical background, the general form is where the wave equation can be derived from physical principles such as Newton's law for mechanical waves or Maxwell's equation for electromagnetic waves in one special dimension, which is given d square u over dt square equals to c square d square u over dx square, where uxt is the wave function which could represent displacement, pressure, or another physical quantity depending on the context. C is the speed of the propagation which depends on the property of the medium, such as tension and density for a string or permittivity and permeability for electromagnetic waves. In higher dimension, for instance, in 3 dimension, the wave equation becomes d square d square u over dt square equals to d square. That symbol square u where is the Laplacian operator, which is in 3 dimension, is like I already wrote in this article, and also for derivation 1 dimension case, consider a string under tension T with linear mass density mu. This small segment of the string experiences forces due to tension. By applying Newton's second law, we obtain the wave equation for the transverse displacement, where you can see this is the equation for 1 dimension case, and we're dividing through by triangle x and rearranging gives the wave equation, and it will give you this equation, and here c is equal to square root t over mu is the wave speed. And for classification, Sound waves are longitudinal mechanical waves that propagate through a medium, which is solid, liquid, or gas, by compression and ref rarefaction. Understanding sound waves involves examining their generation, propagation, and reception, as well as the physical principles governing this process. Nature of sound waves. The first one is longitudinal waves, which is the particles in the medium oscillate parallel to the direction of wave propagation. And also compression and refraction, which is the region of higher pressure, which is compression, and lower pressure, which is refraction, travel through the medium. Parameter of sound waves, frequency, the number of oscillation per second, wavelength, the distance between successive compression and refraction, amplitude, the maximum displacement of particle from the equilibrium position related to the sound's loudness, speed t, the speed at which sound wave travel through a medium influenced by the medium's properties such as temperature and also density. And for the speed of sound, where the equation is C equals to square root B over rho, which is B is bulk modulus and rho is for the density of the medium. In air room temperature, which is 20 degrees Celsius, the speed of sound is approximately 343 millimeter per second. Wave equation for sound waves, as I already wrote in this, which is d square b over dt square equals to c square, and where the pxyzt is the sound pressure at position xyz and the time t. C is the speed of sound. And the revision for physical principle is the first one is continuity equation, which is for a small volume element in a fluid, the change in density, which is rho, is related to the divergence of the velocity field v, like this equation. And also for small perturbations where the density change, triangle p is small, this simplifies to this equation. And for Euler's equation describes the motion of fluid element under pressure forces, and the equation given like this. And also for a diabetic process, in this process in this in this one, we assume sound wave propagate adiabatically without heat exchange. And the equation given like this. And combining this equation and eliminating intermediate variables leads to the wave equation for the sound pressure, which leads to this equation as you can see. And for the sound wave propagation, reflection, and transmission, when sound waves encounter a boundary between two media, part of the wave is reflected and part is transmitted. The behavior depends on the acoustic impedance of the media, which is like this equation that I already show you, where rho is the density, c is the speed of sound medium in the medium. For diffraction, sound waves bend around obstacles and spread out after passing through small openings. This phenomenon is significant when the wavelength is comparable to the size of the obstacle and opening. And for interference, when two sound waves meet, they interfere constructively or destructively, depending on their phase relationship. This can result in patterns of increased or decreased sound intensity. Per Doppler effect, the observed frequency of sound changes if there is relative motion between the source and the observer, which is like this equation, as I already write this, where F apostrophe is the observed frequency and F is the source frequency, V naught is the velocity of the observer relative to the medium, and V source is the velocity of the source relative to the medium, which is Vs V naught. P apostrophe and F apostrophe and F. The wave equation for sound waves is the second-order partial differential equation that describes the propagation of sound waves through a medium. The general form of wave equation in three dimensions is, as I already wrote this, and for the solution methods for this wave equation in sound waves, as the first one is we use a separation of variables, which is this method assumes that the solution can be written as a product of function, each depending on a single coordinate. For example, in one dimension, we let dxt equals to xx dt. Substituting into wave equation and separating variables yields to ordinary differential equation, which is ODEs. And the second one is Fourier transform. The Fourier transform converts the partial differential equation PDE into an algebraic equation in the frequency domain, which is easier to solve. The inverse Fourier transform then gives the solution in the original domain. The third one is the Alembert solution for 1D wave equation, which is for the one-dimensional wave equation. The Alembert formula provides a general solution as this, like this, where f and g are arbitrary functions determined by initial condition. And the fourth one is Green's function. Green's function provides a way to solve inhomogeneous differential equation. The solution is expressed as the convolution of the Green's function with the source term. Finite difference method. This numerical method discretizes the wave equation in both space and time, converting it into a system of algebraic equation that can be solved iteratively. This is the example of separation of variables in one dimension. Consider the one-dimension wave equation, and this is the original equation, and we assume x equals to xs, like I already said from the top, where we substitute into the wave equation. And we divide both sides by c square xx dt, where we can get this after we divide both. And also, since the left side depends only on t and the right side only on x, both must equal to constant stay. In bracket, negative k square, this gives 2 ODs, which is d square t in bracket t over d2 square plus k square c square t, and also in bracket t equals to 0. The solution to this ODs are t in bracket t equals to a cos in bracket k in bracket t plus b sine k in bracket t. Thus, the general solution is pxt in bracket c cos kx plus d sine kx multiplied by a cos k in bracket t plus b sine k in bracket t. The initial and boundary condition. To fully determine the solution, you need to initial condition px0 as well as appropriate boundary conditions such as p0t and plt for a domain length. Each method has its strength and it's suited to different types of problems. The choices of method depends on the problem's complexity, initial and boundary condition, and the desired form of solution. For the conclusion, in conclusion, solving the wave equation for summaries involves various methods tailored to the problem specifics, such as initial and boundary condition, analytical methods like separation of variable Fourier transform, and the Alembert solution provide exact solutions for idealized cases, while numerical methods like the finite difference method offer practical solution for more complex real-world scenario. The choice of method depends on the problem's complexity and the required precision balancing between analytical elegance and numerical practicality. And this is the references that I got for this article. And that's all from me. Thank you. Thank you.